We're going to talk about the statistical study of the CMB anisotropy. Cosmological theories can be checked by a statistical study of CMB temperature uh, across the celestial sphere. The temperature at angle theta and phi, with the average value integrated over the solid angle. That should be 2.725 Kelvin. The temperature fluctuation we're talking about is the deviation from the average temperature at the location theta and phi. Has a root mean square value, okay, turned out to be about 1 part in 100,000. So that's the amount of anisotropy we see. Now, how do we describe such a temperature variation and connect it to the underlying cosmological theory? I recall that for a function of one variable, a useful approach is Fourier expansion of the function in a series of sine and cosine waves with frequency that are integral multiples of the fundamental frequency, which is the wave with large wavelength. Similarly, we can expand the temperature fluctuation in terms of spherical harmonics. You can think of it as the vibration modes on the surface of elastic sphere. Okay, so here's the temperature fluctuation expanded in terms of spherical harmonics, and here's the coefficient expansion. Okay, L go from 0 to infinity, and the m value goes from minus L to plus L. So the multiple number L represents the number of nodes, location of zero amplitudes between the equator and the pole, and while m is the longitudinal node number. For a given L, there are 2L plus 1 value of m going from minus L to minus L plus 1, so also until plus L. The series can, of course, be inverted, so that the expansion coefficient A sub Lm can be expressed in terms of temperature fluctuations. Okay. So the cosmological theory predicted statistical information about the temperature fluctuations. The most useful statistic is the two-point correlation. Consider 2 points in the universe sphere located at n1 and n2, separated by angle theta. We define the correlation function as the average of the product of temperature fluctuation at n1 and n2. Okay, it was n1 dot n2 to be cosine theta. The inflation cosmology predicts the fluctuation Gaussian. That's maximum random, so it's independent of ALMs. Okay, namely, the multiplier LM are uncorrelated. For a different value LM, the average L equals 0. The 2 product of A star A is vanished if L not equal to L prime, M not equal to M prime, and the coefficient here is C sub L, which defines this defines the power spectrum C sub L as a measure of the relative strength of the spherical harmonics in the decomposition of temperature fluctuations. CL measures the typical size of temperature irregularity on a given angular scale. The lack of M dependence reflects the rotational symmetry of the underlying cosmological model. When one plugs in this, it was plugged this from the last slides, del T over T in terms of spherical harmonics into these correlation functions, and with the condition that they average out to 0 and 2.2. So from this, we can find that that's the two-point correlation can be expanded in terms of Legendre polynomial with coefficient expansion simply the CLs. Okay. So this carries information about space of a multiple number L. We just note for large L, the Legendre polynomial goes like cosine L theta, so the peaks are located roughly at L equal to pi over theta. Okay. So the angular power distribution, so plot C sub L, which is a convenient uh, uh, scale factor, and it's in functions L, you get this kind of curve. And the power spectrum can be measured by observations and compared with theoretical predictions. We know the base of the prominent features. It's a very flat low L value. Here's ever increasing L. For low L, this is sort of the so-called the Sachs-Wolf plateau. Due to the variation gravitational potential, it should be a very smooth dependence at the last scattering surface. And then there's a whole series of oscillations, sometimes called baryonic uh, acoustic oscillations. These coming from the complex motion of the cosmic fluid when the CMB was first created. And then the damping tail for large L simply reflects the finite size of the last scattering surface. Okay. The theoretical prediction, for example, this red curve, is made by selecting cosmological parameters that yield the best match of the observed power spectrum. The Causal parameters are used in our presentation. Like, for example, we talked about the Hubble's constant and the density parameter for matter, for various things, are obtained by actually by the CM, W map and Planck uh, observations. Okay. So from these observed anisotropy, we can obtain the cosmic parameters from the angular power spectrum. Okay, when looking at so when we're looking at anisotropy distributions like this, we see spots of many different sizes. This pattern can be translated into a power spectrum, which encodes the key cosmological information that can be compared with theoretical predictions. So you look at this because that represents the various cosmic parameters to produce this curve, and that can be compared with the model you have. Okay. We know that the first most prominent peak is at L roughly equal to 200, and so it corresponds to an angle separation of about 1 degrees, which you will see tells, but directly related to the fact we say the spatial geometry is flat. So this ends the second part of lecture 27.